At this point, I just want to take a few minutes and review some of what we should have learned and add a little bit to it. So we're going to focus on the 3D printing technologies, methods, and materials. Additive manufacturing in the past, we'd make clay, build our pots, put our corn in it, survive the winter. So in this lesson, we want to take a quick look at what's a definition of additive manufacturing and the characteristics, what 3D printing technologies are available that we have looked at, what are digital materials, and determine which 3D printing technology to use for the application. So what does additive manufacturing mean? It's a process for making a 3D solid object by adding material, or a process of joining materials to make objects from 3D model data, usually layer upon layer. So 3D printing is the fabrication of objects through the deposition of material using a print head, nozzle, or other printer technology. The term is often used synonymously with additive manufacturing. And what should be stressed is, yes, 3D printing and additive manufacturing terms are often interchanged, but they are somewhat different, as 3D printing is just one form of additive manufacturing. Typically, we're going to start with a CAD model, and once we have our 3D model, we have special software that will slice it into layers, figure out if it needs support, and how to fill the inside surface of the part. All three of these working aspects appear in various forms in all 3D printing technologies. There may be difference in the slicing resolution, the support material, or fill options, but all three are used in various forms. So next, we just want to review the different 3D printing technologies that we've already touched upon. It's important to note 3D printing technology has been around for 30 years now, but it only recently did it come into its own and start to be used more frequently in manufacturing. And here's a quick look at the various laser melting technologies. And the advantages of the laser system are that you can manufacture parts in standard metals with high density. A constantly widening set of standard metals is available. Parts can be further processed. The disadvantages of the laser styles are the technology is slow and very expensive. The tolerances and surface finishes are limited, and the materials are incredibly expensive. When it comes to the laser mounting technologies, it's often used for prototype, support parts, small series of part runs, and tools for injection molding, such as can be seen here. The LMD, or laser metal deposit manufacturing, as seen in these two pictures, deposits the material in a process very similar to welding. The powder is fed into the head where the laser beam cures it or hardens it. The advantages is that parts can be manufactured in standard metals with high density by electron beam melting. However, the availability of materials is limited and the process is slow and expensive. So parts in standard metals with high density and good mechanical properties can also be made. Requires less support structure compared to laser melting, and it builds parts that are very similar to the laser melting technologies. The disadvantages are the electron beam is slow, expensive, and works with the limited set of materials. Parts usually require a lot of post-processing. They'll need to be cut physically with a saw off of the build plate, and they do not achieve the same surface finish as laser melting. The laser deposition technology is typically used for prototypes, support parts, production parts, small series runs, and tools for injection molding. The applications include prototypes such as we see here, which are typically made in standard metals to test for form and fit and functional testing. Support parts for jigs and fixtures can also be produced with this method. Electron beam melting, similar to laser, focus the electron beam on the liquid bath of the metal powder to cure or harden it. In this process, a thin layer of metal powder is selectively melted by the electron beam, and parts again are built up layer by layer in the powder bed. Electron beam melting is similar to laser melting, but it works with electron beam instead of laser. The machine distributes a layer of metal powder onto a build platform in a vacuum chamber, which is melted by the electron beam. The build platform is then lowered, and the next layer of metal powder will be coated on the top. The process of coating powder and melting where needed is repeated, and the parts are built up layer by layer in the powder. Electron beam melting does require support structures, which anchors the part and overhanging structures to the build platform. This enables the heat transfer away from where the powder is melted, which reduces thermal stress and prevents warping. The build envelope can be filled with several parts which are built in parallel as long as they are all attached to the build platform and the parts are built under a vacuum. The advantages of electron beam melting include that the parts can be manufactured in some standard metals with a high density. Parts in standard metals with high density above 99% with good mechanical properties can be produced, and it requires less support structure when compared to laser melting. Builds are faster as well when compared to laser melting. The disadvantages are the electron beam is slow, incredibly expensive, and it works with a limited set of materials. Parts usually require a significant amount of post-processing, and it does not achieve equally good surface finishes as laser melting. Applications for electron beam melting include small series parts, prototypes, and support.